Recording starting. I have slides. You still see the slides? Nice. All right. So I'll be talking about SNARKS and STARKS Part 1. I'm excited that I actually get to do 2 sessions with you all. I think I'll present again next week, which means I think next week will be really awesome because we'll go into much more detail. This week I kind of want to catch everyone up, get people on the same page, and we'll still go into some detail and do some interesting things. So my name's Porter. I'm a protocol security engineer at Matter Labs. Matter Labs is one of the teams building ZK Sync. That's pretty much all I'm going to mention about ZK Sync for the presentation. If you have questions, let me know about us. I'll say a little bit about our proof system, but in general, this is like a general talk about SNARKS and STARKS and kind of what's going on in the world today. Thank you, IIT Delhi, for having me. I know you guys it's a really good school, really cool people. So it's I don't know. I give a lot of talks, but it's a big deal for me to get to talk to you all. So thank you. All right, overview. Cryptographic proofs solve the re-execution problem. We'll start just basics, just in case. We'll get past this quickly. So re-execution is you do some computation, or how about this? I do a computation, and I give you an answer, but how do you know I actually did the computation correctly? Maybe you trust me, but if you don't trust me, you have no reason to believe that the answer I give you is the correct answer. The naive solution to this is you should just redo the whole computation yourself, and that's kind of not very good because then what's the point? You can't outsource anything. You have to redo everything in the world that you care about on your own. It's no good. So we came up with these cryptographic proofs, and I'll talk more detail. Just briefly, common uses that you've probably seen: privacy, Zcash, Monero, Aztec, scaling computation like ZK Sync, and then there's a lot of cool ZK projects that I'm extremely excited about actually. ZK TLS, ZK P2P, ZK email, web proofs, they're all kind of, it's all different names for basically the same thing, but the idea is to take right now the first two are what everyone talks about. They're the big use cases, but they're very blockchain centric. And the third one is about taking any computation on the entire internet and proving it to someone else, which leads to really insane things. This is not a talk about use cases, but I think that one's really great. And if you haven't looked into any of these before, please do. This is actually I think it'll completely change the entire internet. I think this is the biggest use case of ZK eventually. Types of cryptographic proofs. Okay, so Vitalik had this on his blog. I don't like this chart very much. So a couple points. First, top left, STARKS, somewhere in the middle of Plonk. Those are things you probably heard about. Dark is not used in practice too much, but very cool. And then previous SNARKS mostly refers to Groth 16, might be the name you've heard before. All right, things that don't make much sense to me are, well, I don't know. And the bottom axis is proof size, but smaller is better is off to the right. So as you move to the right, proof size is getting smaller instead of bigger. It's a little weird. But then there's quantum secure for STARKS. Arguably, in practice today, basically no one's at a security level that's safe enough. There's also questions about whether the hash functions we're using are quantum safe. In theory, you could make a STARK that is quantum safe. In practice today, I don't think anyone goes quite far enough to do that. And then yeah, as far as security assumptions, STARKs are just based on the fact that hash functions are one way, versus Blanc and other things are often based on elliptic curves, which there's kind of two camps on this. There's the people who think elliptic curves are too complicated, you should just use hash functions, and the other camp is that elliptic curves are cool, pretty much, and they work well, and they actually have a ton of cool properties that you can't quite replicate with hash functions, or it's not the same. Cool. So basics on building a proof system. I think you're probably all familiar with this already, but somehow you can break the proof system down. The left side breaks into arithmetization step and polynomial commitment. And then this is the third piece, which is the actual polynomial interactive oracle proof on the right. But basically, you need to convert whatever problem you want into like a ZK friendly format, and then you need to do like an interactive oracle proof or something, but you need like some argument that you're doing the computation correctly, and then almost always you end up with some polynomial, and the polynomial commitment scheme is how you actually like save time for the verifier. So there really should be 3 steps, but all these diagrams are like leaving one of the 3 out, which is a little annoying. So part of my talk today is to like, I don't know, clear up some things where if you just like read all of the blogs or the posts, it's easy to like, I don't know, miss something because the posts kind of like don't quite get it right. Cool. So, oh yeah, so if you want to build a proof system, you can almost pick like any arithmetization you want, any like argument you want, and then any polynomial commitment scheme you want. So there used to be like very clear lines on like this is a Stark, this is a Snark, and now it's kind of all getting a little more blended together because people are just picking and choosing like the best parts of Starks, the best parts of Snarks, and like the best arithmetization, the best arguments, the best polynomial commitment schemes, and just mashing them. Snark versus Stark, what's actually the difference? There's a really good blog post by Justin Thaler from A16Z about 17 misconceptions about Snarks and why they hold us back. And I encourage you to read the whole thing because I think you'll actually learn a lot by all of these misconceptions. The one I want to clear up now is, I think it's like number 3 on his list, which is, yeah, Snarks versus Starks. So SNARK stands for Succinct Non-Interactive Argument of Knowledge, and STARK stands for Scalable Transparent Argument of Knowledge. So argument of knowledge is the same on both of them. It's we're going to prove that we know like the witness value, which is like the input value to solve some hard problem, and usually you can all and the whole like thing is set up so that the only way I could possibly know the witness is either a very, very, very lucky guess, or I've actually done the computation correctly. So there are all based on probability. I guess it's like a small caveat, but you can make the probability like as high as you want. If you wanted like perfect information, you just have to redo the computation. So getting 99.9999 with like 128 bits of security or whatever security level you want is very good for all real use cases. Anyways, differences here. So Starks technically don't have to be succinct. Succinct's only on the Snark side. So a Stark can have, a lot of times this means the proof size can be quite large, and that actually ends up being a pain for a lot of blockchains. So zkSync uses a Stark proof for like the big computation, but it's like too much data. But like the actual just proof size is like probably hundreds of kilobytes, which is a ton of data to post on Ethereum. And so instead, a lot of people use SNARKs at the last minute, and you can prove anything. So you can use a SNARK to prove a Stark. You can use a Stark to prove SNARK. And so that's called like wrapping or aggregation. Excuse me, my voice is a little messed up. All right. Yeah, aggregation. Anyways, the other difference is that Starks technically don't have to be non-interactive. You could have an interactive proof and it would still be a Stark. In practice, everybody today, geez, I need some water or something, but I'm trying to struggle through. in practice today, everybody using a Stark definitely does it non-interactively, because having to interact with the verifier is like actually a painful process. Like you both need to be like online, or you need to like go back and forth. Like it's annoying if I want to prove something and I have to wait for you to respond, and then I send you back something and I wait for you to respond again. And a lot of these protocols we do like maybe 100 rounds. So I don't want to go back and forth with you 100 times. Like non-interactive is much better in the real world. Um, yeah. Okay. So that's people get very confused and caught up over these differences in practice. Or I don't know if we're being rough and like casual about it. I think we should just count all Starks as a type of snark and just move on with our lives. But theoretically, if we want to like stick to what the academic papers originally defined, these things are like there's some differences that mean they're not quite the same, but it's also not worth like getting too caught up because everybody mixes and matches things these days anyways, so we move on. So arithmetization step, very important. This is kind of, in my mind, like what comes first is taking what you want to prove, which is just very abstract, like some computation, anything, and we need to convert it to a nice format for zero knowledge proofs. Now, yeah, if you want to prove every single step of a computation, you're going to have to write out every single step, and that's like quite painful. And that's one of the main reasons why like the overhead for zero knowledge proofs is like kind of large, because a lot of times you just have to write out like every single step and save every single step and then prove every transition. I'll kind of get to it, but arithmetization, if you want the whole like protocol to be fast, arithmetization is like a very important step to make sure there's not too much overhead. So the way that I like to understand arithmetization is from the perspective of the execution trace. The execution trace is a name for like an array, a two-dimensional grid. And each row in the grid is the state of all the registers at some point in time. If you're doing your computation like register based, which is how most of the proof systems work. Some companies actually do different things, but it's easier to understand it this way. So if like at starting point you got like a 1 in the first register and zeros in all the other registers, then the first row in your grid will just be 1 0 0 0 0 all the way down, and then each column is like the state of the one register over time. So the first column is always going to have all the values from the first register over time, and we'll do a little more concrete example on the next slide. What the trick is then, like why do we want to arrange all of these values in a big grid, is we can consider the columns as polynomials. So let's say, I'll flip back and forth actually between this and the next slide. Let's look at Plonk quickly, and then I'll get back to how it like works with the grid. So in Plonk, the setup for these equations is as follows. This snippet is from Vitalik's blog post on Plonk. I should give him credit somewhere on the slide, but each equation is of the following form. Think L is left, R is right, O is output, M is multiplication, Q is constant, or C is constant. And what we have is there's a bunch of these like Q variables with subscripts times AI, BI, CI, AI, BI, and then the last one isn't multiplied by anything, and then equals 0. It's like the first time you're seeing this looks like really weird. There's like 10 different variables going on. Like what is all of this? They like we're mostly just trying to set up a way to prove that, like, for example, an addition is done correctly. And if we want to prove addition, we can try and set so that the A plus AI plus BI is equal to CI. And we do that by changing the Q polynomials to have the left one be 1 means we're just going to have 1A, right? QRI equals 1 means we'll have 1B, and QOI equals -1 means we have -1C. So A plus B minus C should be equal to 0. And if you pick different, these are called selector polynomials at the bottom, or the Q's are like a selector because it kind of selects which gate you're going to be using. And now, if you kind of abstract all of the Q's as just like what gate am I applying or what computation am I trying to prove in this row, that the whole thing becomes much nicer. So yeah, we have like a left and a right. The constant is usually like the output. We also have the multiplication gate, and then constant gate is for if you ever just want to make sure that like a variable is equal to the number 17. You just put 17, or I guess minus 17 in the constant, and you do like a plus a minus 17 equals 0. Yeah, sorry. Negative signs are tricky. So going back to making a big execution trace out of this, also I should watch out for time. I want to make sure I get to everything. Each like row in the execution trace would just be like the values of well, the Q's, and the A, B, C, AI, BI, and or A times B, and the constant term, and all of those just in a row. And then the next step, we might do a different computation, and then all of those should be in a row. The next step, we do another computation, and all of those should be in a row. So we end up with this big grid. And why do we want to consider these not just as values, but we want to consider the columns as polynomials? The idea is that like if the left column, if A's plus B's should always be equal to C, then instead of having to check that, say there's like a million rows in my execution trace, if I do like a million addition problems, I don't want to check a million different things. What I want to check is that the whole polynomial of the first column plus the whole polynomial of the second column is equal to the polynomial in the third column. Or yeah, A column, A plus B equals C, just the polynomial. That way I can check entire columns at once. And even though my row, I have like a million rows, I can check all of the columns very quickly. And in practice, because of like fundamental theorem of arithmetic, you can just randomly check the polynomials at one point, and you get like pretty well convinced that the polynomials are the same. So even if there's a million rows, the verifier can then check like all 1 million rows by making polynomial, or the prover has to make the polynomials and send them over, but the verifier can check those polynomials at just one point, and so it's very easy to check that all 1 million additions were done correctly, and the verifier only has to do one addition to check it. I have a lot of words, sorry, but hopefully it's clearing things up. The table is like, I think, very critical to understanding sort of like why are we putting these things in the word format, and then this is kind of the actual meat of the argument, the constraints. This is like people, for some reason, when they talk about ZK, tend to leave out like the actual argument that you're using, but the argument and the constraints are like the main thing that's going on. So there's, I'll talk about two specifically. There's algebraic intermediate representation. You have, this is what SNARKS use, and the constraints, you can think of them as two different types of constraints. We have boundary constraints, and also this is from Chrono Kirby's blog post. I think yeah, he's public with his name. His name's Lucas. Is great. He works at Penumbra. And anyways, boundary constraints. On the left, you just want to say that at some point in time, this register is equal to this value. And then transition constraints is saying that like this state is like a function of the previous state. And so a lot of especially the transition constraints, you can get really fancy with, it doesn't actually have to be the previous state. You could say this state is a function of like the state after it. Like like the math lets you do anything you want. You need to make sure it actually makes sense for what you're trying to prove. But it's a very flexible sort of way of constraining. And this way, like, let's go back to think about the whole table. If I can prove to you that, like, at certain point in time, for example, like at the inputs at the top of the table, all the values are correct, and also at the bottom of the table, I would also put like boundary constraints that the outputs are like what you expect, and then I would put transition constraints for like the whole rest of the table, shows that like every transition starting all the way from the inputs and the outputs is correct. And this way you're convinced of like the whole thing must be right because I've checked the inputs, every transition, and the outputs, so we're done. Nice. That's like the start argument pretty much. Okay, list of gates. This is actually what we use inside zk-sync's proof system Bootcamp. We're going to use Plonk-ish gates. Actually, I should go back and mention one thing about Plonk. One of the reasons people really like Plonk is because here we have like 5 columns of like left, right, output, multiplication, constant. But it's very easy to just add another column for like any strange computation you want. So if you want a column that's always like, you know, a squared times b plus c, like you could put all of that in its own column every single time. Now, for like, then you start getting to like, is it efficient to like, you're adding a whole new column to your table, but maybe that new column lets you like have fewer row constraints. Like doing everything just in terms of like addition and multiplication can be like quite slow. So if you always know you want to do like cubics, then you like it's better to just add a cubic like column instead of having to multiply 3 times in a row every time. Okay, so that's how you get Plonk-ish. And then for zk-sync, we've added basically all of these gates for addition, subtraction, like reducing, like modulo, matrix multiplication, and then fancy ones like Seiden hash function is like a quite complicated gate, but yeah, you still just have like a list of inputs, and then like Seiden happens, and then you have an output hash. So in a little more detail, you can check, for example, Boolean. So the way to check if a number is either 0 or 1 is by checking if x squared minus x is equal to 0. And this is like some of the code snippet on how this one works. So on the right side, you see we have num variables is 1. We just have an x. We don't need any like witnesses or constants. Like there's nothing else going on here besides an x. And then for helping like evaluate the gate down below, the constraint degree is 2, and the number of, because there's an x squared term, and then the number of quotient terms is 1 because there's just the 1x variable. All right, so for Plonk, the sort of way you prove it is like here I would prove that for some column, like x squared minus x is always equal to 0, or for whichever values I want. I also need to prove that some of the values are the same between, like, so I might want to check that like the output of one line in the execution is the same as the input into the next line. And that's kind of the Plonk style argument is, yeah, you prove like that each row is valid, and then you prove that just on its own, not like Stark compares between rows basically, and Plonk proves the row is valid on its own. And then Plonk needs to do copy permutation argument to get between rows. And the math, like again, it's like some symbols, but it's really simple. You just want to like prove basically that when you go in a circle, like you end up with the same things. So a lot of these products are like, if you have, it's basically a permutation. check like from math, and so the first permutation will be like 1, 2, 3, 4, and then you want to basically cycle it once, and then or let's say like there's 4 variables, so I should name w, x, y, z. That's better. And then what I want to check is if w, x, y, z, and then I cycle it once, and so I get z, x, y, w. And if I compare each of those, and like they should all be the same if like this whole cycle, like if x equals y, if x equals y equals z equals w. I said that a little poorly, but you guys get the point. Prove one row at a time and between rows. There's the third special argument that works for STARKS and SNARKS. Well, you'll have to pick one that actually fits with your protocol, but a lot of teams have figured out we need a lookup argument as well. Completely not necessary. You could do everything with just the normal gates and the copy permutation argument, or you could do everything with just the AIR constraints. But if you only have multiplication and addition gates, there's a lot of Boolean operations that you probably want to do. So like XOR appears a ton. Hash functions that aren't built for CK can be very painful to do. So like catch-ack in particular is like hard to prove. Not like hard to prove, but it's computationally expensive to prove because you have to somehow fit a Boolean operations into like standard addition and multiplication. And mostly the way you do that is you have to like bit decompose everything and then like one by one check the constraint, the addition and multiplication on each bit. And that's kind of terrible. So instead we use lookup arguments where we can throw everything into a lookup table. And the way lookup tables work is you can just check quickly that so you'll have again like an array or like a list of values, and then what you want to do is check that the same list already appears in the table. So for the table, what I'll do is I'll generate ahead of time publicly, everyone knows it, that like A XOR B should give me this result C. And then I get like a triple ABC. And then when I'm running through my program, if I ever want to do an XOR result, I can just like magically say, like, here's A, B, and C, and the triple ABC appears in my lookup table. Therefore, like this, like C is the valid output of A XOR B. And so, like a lot of times, the check, the check is based on like dividing in a finite field, and sometimes you shift it a little bit just to make sure that like the prover can't cheat. But again, the math is like relatively like very simple. So like don't be afraid of moon math. It's actually really not bad. I think what's bad is the list of resources to learn about it. I still, including myself, I think like no one's made like great explanations for a lot of these things. But it's not complicated, I promise. We're just bad at explaining. List of lookup tables that we use in zk-sync, just to get a picture. We have an AND table, AND or XOR, byte splitting. Range checks is another very common one. We need to make sure, like, if you do some payment, that you have like enough balance in your account, so your balance falls in some range. Yeah, it's like the common thing you need to do is like make sure a value falls like in some range. And it's way better to do with a lookup than to try and figure out how addition and multiplication. You have to like check every single value in the range is terrible. Oh, and also for SHA-256 again. Cool. So this is from Vitalik's blog. He's finishing off summarizing how Plonk works, and so this is kind of like the final steps, but I'll walk through it one more time just to like solidify. Hopefully by now a lot of this, like, you just nod your head, you're like, all right, Porter, we get it. But finish off, go over the scheme again. Given a program, you convert it to a circuit. and then generate a set of equations that look like that. That's going to be your rows. And then you convert the set of equations into a single polynomial equation. So you consider the entire column as one polynomial, and then you just have to do this check on the column polynomials. You also generate a circuit, a list of copy constraints, and then you have to do the permutation check. And it talks about the cofactor H is when once you've done all of this math, you kind of want to make sure that for Planck that you get a bunch of zeros at specific values. So like every row in Planck evaluates to 0, like as you can see at the top of the screen. And so what we get is actually some random polynomial. We know it's supposed to have zeros at certain places, and so we there's a last trick where you like divide by you have some polynomial and you divide by everywhere you know that it's going to have a 0, and then you have this kind of leftover matrix H, or leftover polynomial H. Yeah. There's a set of equations between the polynomials that needs to be checked. You can do this by making commitments to the polynomials and opening them at some random z, along with the proofs that the openings are correct. Running these equations on these evaluations instead of the original polynomials. The proof itself is just a few commitments and openings. It can be checked with a few equations. That's all there is to it. So, yay! All right, so that was Planck. We looked at Stark arithmetization as well a little bit. And so hopefully you're getting a feel for like how these protocols really work, and then you can start debating the theoretical stuff of like that. A lot of the variations too, I should mention, of like, yeah, Planck-ish just means you have more columns. There's turbo Planck. There's FF Planck is actually something we're adding at ZK Sync soon, which is FF is from fast Fourier, and you can do a trick where here at the end you still have like several polynomials that you want to check, and instead of having several polynomials, you can kind of merge, and if you have like 5 polynomials and 5 checks, instead you could just merge them into one polynomial that's 5 times as long, and then maybe you can just do one check. And because the verifier does not have to the verifier only has to do one check, it's better for the verifier. It might be a little harder for the prover because the prover has to put like 5 different polynomials into one big 5 times as large polynomial. And it does that through something like the fast Fourier transform. And so, through the same idea as the fast Fourier transform. So that's how you get with FF Planck. So there's all these sort of like minor variations that don't really change the big picture. There's just like a lot of optimizations that we figured out over the years. So it's hard to keep up with like all the research actually that happens in ZK, but a lot of it is like minor variations on similar stuff. I have another slide on this in a second on the current research. Last part about recursion. A lot of times for efficiency, you'll want to design a circuit specifically for one problem. So we design a circuit specifically for SHA hash functions, and then we can like tailor that for SHA. And in SHA, like the efficiency doesn't get in the way of like everything else we're trying to do, and then we just recursively prove that all the circuits are valid. And you have to be like a little careful. There's like some edge cases where you need to make sure that like every SHA was actually proven some way. So you need to like kind of pass things between the base layer circuits a little bit. Regardless, yeah, you do recursion. A lot of times, even after recursion, you do a compression step, which is like ZK Sync, we're using a Stark in the first half because Starks for now seem to be the fastest for the prover side. And then SNARKS, like Planck, seem to be the fastest in practice for the verifier side. So we'll wrap the Stark into a SNARK and we get the best of everything and we're all happy. All right, good resources for ZK. I referenced some of these in my talk, but blogs, Vitalik's blog, He's actually the best, I think. And he has several on Clonk, SNARKS, like Fry Protocol. He has several. And then A16Z Crypto. There's only 3 books like in existence on ZK, and I'll talk about the differences. I think Justin Thaler's is probably like what I would recommend overall. I think he is very focused on what's it called? I forget his favorite proof system name. I'm blanking. But yeah, Justin Taylor is probably the most like well-rounded book, I would say. Like Alessandro Chiesa and Yogev just came out with a SNARKS book that I have not seen many people talk about. It's very like academic. If you like all the formal definitions and like slow step-by-step like methodical, well, not slow, but like it's very academic and theoretical, but it's a very good book. And then sort of on the opposite end of the spectrum, Least Authority Moon Math Manual is it's actually like 4 or 5 years old, so it's like extremely impressive that they wrote all of this that long ago. I think it's Least Authority is actually made up of some Zcash people, which explains why they were so good so early. And then I guess small like history lesson, because I think it's good for everyone to know like a little bit of the history of the industry. Zero knowledge proofs were like first like academically talked about by Xavi Goldwasser, Sylvia Macaulay, like I forget, like in the 80s or something. In practice, nobody used them until Zcash came along in like early 2010s, and like Zcash really changed the world for ZK. They showed everyone that hey, this is stuff that's like useful in practice, and they actually just went out and did it. And so like Zcash will forever be like heroes of like making sort of ZK a reality. I think they don't get enough credit for that. All right, sorry. History lesson done. Videos, ZK MOOC, all the like top professors got around and like made some videos on this. Justin Thaler's actually in some of them. Dan Benet, big names you know, and then ZK Hack has like a lot more videos. And I particularly like whenever like some new system comes out, a lot of times they'll get an interview on ZK Hack and explain it. So if you prefer listening to videos or just want to get like the main idea, ZK Hack's great. Current ZK research, smaller fields, Circle Stark and Binius. So elliptic curve, one of the disadvantages to Snark, like elliptic curve based proofs, is that elliptic curve field sizes are fixed. Like you can't you can't change the field size of the elliptic curve. It has whatever size it has. With and to be secure, you need that field size to be like 256 bits or something, which is not like massive, but like it's kind of large. What we've been doing in recent years and with a lot of Starks, particularly Fry, is moving to smaller fields. So zkSync, Polygon, a bunch of teams are, and Starkware obviously, are using like 64-bit fields. Some people are even moving down to the Mersenne prime fields, 32 bits. And Binius is switching from prime fields to binary fields. It's not clear exactly like if Binius will be faster yet than the prime field stuff, but it's cool research. And then because I should say the fun idea about Binius is like, let's say you're multiplying like two Boolean numbers together. If you have to store those 1 bits in 255-bit like slots every time, like it's kind of terrible overhead. But like more practically, a lot of times you're multiplying like 1 byte at a time. It's like a U8, and you're storing a U8 in like a U256 every time for your field size, and that's also very, very bad. What Binius does is use like actually a tower of binary fields. So if you multiply U8 by U8, it only stores those like in U8s, and so you could just prove that part in a U8, and then when you like multiply by U256, you prove that part in then like a bigger field. So Binius is really cool. ZKP overhead is another area of ZK research. I mean, pretty much everyone's working on this, but how many times more expensive is generating a proof compared to normal computation time when ZK Zcash proofs are like relatively small because you're only proving a local transaction. But I would say like in general, ZK used to be at close to like 1,000,000 times overhead. So if you do a computation on your computer, it takes 1 second normally. If you try and prove it in ZK, it would take 1,000,000 seconds. So it's like not so great. With new advances, especially the GKR proof system, and follow the ZK AI people, ZKML, they're actually, because ML is so computation heavy, the ZKML people are like working the hardest on the ZK overhead problem, and they've got it down to like 100 times overhead, is the last I've heard. So from 1,000,000 times overhead to just 100 times overhead is like really good, and hopefully, actually, people like almost every ZK researcher still believes there's like 10x improvements to be made still. So the dream scenario is that the ZK overhead gets down to like maybe it's twice as bad as just doing a normal computation, and then like at that point you can just like ZK the whole world because like processors are so fast anyways that a 2 times slowdown is like not even that big a deal if it's like 0.01 milliseconds, and now it's 0.02 milliseconds. We're all chilling. Last point is like phones versus huge servers. Like client-side proving is the buzzword, but privacy ZKPs need to be generated like on a phone or in someone's like web browser versus something huge like ZK Sync. We have tons of transactions, and it's fine to prove all of them in just like one massive cloud computer. Now, so far in ZK, like a lot of people had been using just the same proof system for both of these, but I think there's lots of room to tailor the proof system you're using to the use case. So I think Aztec is actually doing well on this. They are trying to pick a proof system that's specifically better for generating on phones or web browsers compared to just the mightiest massive one that we need for ZK Sync. All right. Thank you. I'm happy to answer any questions. Next week, I want to talk more about Fry in particular, some of the security analysis, and then some of the real world details that I didn't have time for. So, cool.
Yeah. Hey Potter, we have a couple of questions and messages.
Yes. All right. SumCheck, Jolton Lasso. Yes, SumCheck was the one I was forgetting. Thank you. That's Justin Thaler's favorite proof system. The like nice thing about SumCheck is the prover time is like linear in what you're trying to do, so it's like theoretically optimal. And also it uses like multivariate polynomials to polynomials with multiple variables instead of like one polynomial with like a bunch of degrees. Nice. Circle Starks. Yeah, what are they're calling it like Stew S2. Yeah, Ellie Ben Sasson, Circle Stark, and Stew. Yeah, you got it. What is multiplicative group and why do we use it in a Stark? We actually use it for both Stark and Snark a lot of times. So the multiplicative group refers to. Let me change the slide. Also, sorry, I wasn't answering questions along the way. I have my slides full screen, so I didn't see the chat. Actually, it's this part. If you look here, or I don't know if you can see the mouse. The bottom of the screen, rather than having a column of list of values, our column is now polynomial. We get values of the trace by evaluating it at successive points. And normally, like if you were to, I don't know, if I was making up CK right now, I would think that I would have the first row be like value 0. I would have 0, 1, 2, or like ff0 is the first row, ff1 is the first, next one, sorry, off by 1. But anyways, you get the point. Instead of 0, 1, 2, 3, 4, we actually use like omega to the 0, omega to the 1, omega to the 2, where omega is like a generator of the finite field that we're working in. And the reason this is used is that it's basically just an optimization thing for if you end up doing some sort of like fast Fourier transform trick or something else, like ordering the field by like addition 0, 1, 2, 3 ends up not being as like efficient as ordering the field by multiplication of some generator element. So that's what like the multiplicative field comes from. Hopefully everyone's heard me speaking. I don't have music. Backdrop is verifier time for some checks because it is logging in. Yeah, the verifier time for some checks is like a little bit larger theoretically, but like a lot of the theoretical stuff has like not ended up like always being real in practice. So what I'm saying is the like big O computational times are like not always in line with like in practice how long it takes to run something. The most obvious difference being that some things you can like parallelize very easily, and if you can like do parallel computation, that helps a lot more than like a slight log factor in a runtime. So, but yeah, so there's like theoretical trade-offs, but in practice, like we're using Fry is like fastest for the prover, even though like Fry like is theoretically not the fastest like polynomial commitment scheme, but like practically it seems to be. Lambda class blogs about Plonk, SumCheck, Justin Thaler. Oh, Rare Skills ZK book is really good. Yeah, there's a ton of good resources too. Lambda class is amazing. They've done really good work for ZK Sync actually, particularly around ZK stack and rolling out new ZK chains. And also like recursive verifying, precompiles. Lambda class has done a ton for ZK Sync. And then Rare Skills, I met Jeffrey at East Denver this past conference. And yeah, he's really good at explaining things. I like Rare Skills too. More blogs. Yeah, Lambda class, IPA, polynomial commit schemes. Yeah, IPA is like inner product argument. There's so many. There's a lot to talk about. There's a lot of good things. But yeah, hopefully none of it's scary. Like you really can. I don't know like at what point you all are in your quest to learn ZK or work in ZK, but this is all like it's all very doable. There's lots of like little details sometimes, but you can get like the big picture very fast, and then for any like one proof system, you can understand it completely in like a weekend a lot of times. So you can just read the original Plonk paper. Yeah, by now there's like enough resources. All right. I think that's all the questions. I'll stop talking. Thank you for coming. If you have specific things you want me to talk about next week, let me know. I want to make it useful for you all. So if you said this is too easy, tell me. I'll make next week's more difficult. Anything else? And last thing, I do need to apologize. This is a big week for ZK Sync, as you may have seen anywhere. So we're not participating in social media or like me as an individual. I'm like off Twitter and a bunch of things. So yeah, I might be slightly unresponsive, but I do see messages. Twitter is the best place to message me. Anyways, thank you.
Thank you, Potter.
Glad to have you, Porter, here, and we're like really eager to have you in the next session.
Thanks.
And yeah, I think there is a question which is left getting addressed. What are the limitations of current StarkNet implementations?
Limitations of current StarkNet implementations. I have not read enough about S2 Stew, their new proof system that's coming out, and that's probably going to be very interesting. I'd say the Starkware team has some of the best cryptographers, and so I think they will like solve a lot of their problems. The big challenge for Starkware is actually that they were too good too early. Starkware was like the first team to launch a full ZK rollup. ZK Sync was second, but yeah, Starkware originally launched like 4 years ago or something, and there have been so many improvements in ZK since then, and now they have to they basically like technical debt because they like started too early and they built things that today are like not as efficient. But the Starkware team's super talented, so I'm not too worried about them getting the upgrades in and working on better systems. But I will, for next week, look more at Stu and let you know.
Yeah. Thanks for the session, Porter.
Great. Thank you all.